Morena and good morning from level 4 lockdown in Auckland, New Zealand. As you can see, I've tried to dress up for the occasion. It's quite rare that happens now. But myself and Simon are very excited to be presenting some of our research today at CAAA2021 Australasia. And so as you can tell from the title, we'll be talking about machine learning, specifically in Northland, Te Tai Tokerau, in Aotearoa, where we're trying to combine LiDAR and machine learning to find sites. I'm sure a lot of archaeologists can sympathize that archaeological data is quite messy, and this is particularly true when you dig, which is quite rare these days, but we all know that it's quite sparse and fragmentary, small samples of variable scales with unique context. And what I'm trying to get at this point is saying that machine learning is particularly powerful for leveraging these kind of fragmentary data sets and producing new insights. What this slide is showing is a recent paper by Simon Bickler, specifically a certain figure, which talks about how you've got a setup, a black box, and an analysis process within the machine learning workflow related to archaeology. So archaeologists are quite good with the data that they produce to produce a lot of images, text, and geospatial and numerical data. Now, this is ideal, that fragmentary record, to feed it into machine learning algorithms where you train it and you refine it and you run that model to produce results that you verify. Now, I think Simon also argues, and I have to be in agreement here, is that just as LiDAR was revolutionary for archaeology, when that's combined with machine learning, as you can tell from a lot of recent papers, is that it's a powerful tool that it can be used to leverage the massive amounts of LiDAR data to find new sites. Now, you take that to a particular region, that workflow that has a lot of sites recorded, but there's a lot of gaps, as you can see with the top figure. There's about 12,000 archaeological sites recorded, and you have a lot of sites ideal for LiDAR, such as past sites, which have and other earthwork features that have ditches and pits and so forth. And you'll notice that a lot of those sites are missing in the forested areas. So you have a relatively large area that's under forest that's not easily accessible by archaeologists for surveys. Either they're on private land or the terrain is just too rugged. And so the first step is to run the LiDAR and see if you can find sites. But it's a good first pass to run the machine learning algorithm to detect sites, which will be useful to, one, update our site records, and two, just scale up research so it's a more robust process. So what this paper, or I guess this conference paper, is talking about is that we have this problem, which is a massive area under forest, and quite often the research has been focused towards what is the best way to visualize archaeological sites in Aotearoa. Is it PCA? Is it local relief? Is it slope raster? Is it sky view factor? Is it a composite of openness, etc., etc.? And then also there's a second problem as well, is what models are good at detecting these type of archaeological sites in Northland. So you've got those two problems. So if we go from the problem, and we've used this animation to kind of illustrate it, what we're trying to achieve is build a composite of the LiDAR data from which the data is enhanced, at least the LiDAR data, and then the machine learning algorithm identifies an area, enhances those features, and then classifies the individual features. And then we check the accuracy of that result. Now what's the added bonus of this process is that we have a whole suite of features, new sites potentially, and upgrades of old site records, which we can use to kind of reconstruct and create 3D models from, which is just useful for public engagement. And on the second hand, it's kind of useful for thinking about the archaeological landscape of Te Tai Tokerau. So we went with a composite approach where we took the DEM data. Unfortunately, we don't have access to the point cloud data. And from this, we did the common morphological visualization techniques, so slope, local relief, sky view factor. And from that, we created the composite that you can see in the top left, the funky looking image. And this was the base data set which we used to train the machine learning algorithms off. So just for reference, on the left is, as you can see, the heavily forested area. In the middle is the funky looking composite of those three morphological techniques merged together. And you can see a very impressive pass site on that ridgeline with double terracing and a large platform area. And on the right is just a segmentation where the computer is segmenting that composite into objects. So the composite is useful in most remote sensing applications because, one, it's more useful, similar to PCA, for the user to see the features that you train the computer with, so you can identify features. And two, it gives the computer more topographical information to build and train off. What was also really instrumental in this process is going back to known sites, looking at their site records. As you can see, these impressive tape and compass drawings on the left. And then what you'll notice is that you can pick up these features in the LiDAR and you start seeing new features. What you also notice is that a lot of these sites are on the wrong location. So on the top right, you can see the very impressive tape and compass plan with multiple terracing, the ditch and bank and so forth on that ridgeline. But if you look at the red outline, it's in the wrong location. So with this process of finding samples to train the algorithm with, it also is useful for just upgrading existing sites. So using the composite, some morphological visualization techniques, and existing data, so all old site records from ArchSite, we were able to build about a training set of about 30 sites, specifically past sites, that the algorithm will use to find other past sites. But what I'm just pointing out here is that a lot of these sites, there's an offset in their location from what the arrow is showing is that that's the actual location of the site, but its coordinates in the wrong place, and this is quite important for the results. So what we did is that we based the training of known sites, as I mentioned, about 30 sites. We built a training model of that, and we used faster CNN, which is kind of iterative as how it learns, where it breaks down an image into smaller objects and trains on those objects based on the information that we've given it. And it's quite useful and a bit faster than normal RCNN. So again, here is just a workflow of that process where you've got the satellite, you've got the composite, and then you've got the machine MLID, where the machine is identifying those sites from the composite. So those black rectangles is the faster CNN identifying past sites from sites that we gave it. So I'm going to take a bit of time here because this is where it gets interesting. What you'll notice is you'll get the background image of the composite. You'll see the red dots, those are known archaeological sites. Then you also see kind of the pale whitish dots, those are just general archaeological sites, those are pits or middens or so forth. And then you get the black rectangles. So what happened is that the machine was able to identify known sites, so it was able to find those sites again that it knows are past sites. It was also missed a few sites, and I think that's down to the quality in the LiDAR data not being good enough. But then, quite well, it identified a lot of sites on ridgelines that are potentially new sites in this area. So what's really exciting, I think, for most archaeologists is when you find a new site, and to any New Zealand archaeologist, straight away they would look at the composite and realize this is a site, but this is the machine learning algorithm that found the site. And then here it is again on aerial photography data to 2020. So that's quite exciting result. So obviously what's kind of interesting as well is the false positives. Obviously they have to do some field work here, but some of these sites are interesting in the fact that they're on the ridgeline, they look terraced and flat, but it's interesting how sites that have been impacted by eroding get picked up. So maybe that ditch that's in the past site in the training sample is very similar to the eroding, and obviously landform is a major factor here. And obviously as well, when you have exposed areas in the forest, you're more likely to find sites, which is kind of a given. The ways that we think that could potentially increase the model, because our accuracy ratio was only about 60%, is that obviously there's issues with the DEM that relates to Imperial Bayesian kriging, which is a bit smoother and better at removing pseudo noise. combining different and experimenting with different composite models and not just elevation, maybe some form of remote sensing data as well, and flared or so forth. Another thing that we're looking at is increasing the number of training data, increasing it from 25 to 100, because if you read most articles, you need a larger training set. And then also expanding the landforms in the training data, and then go and focus on specific features, not a large parsite, which encompasses a lot of features, but specifically looking either for ditches or pits or so forth. So when we ran the model again, we got it up, like I said, we got it up to about 60%. And what's really interesting is that you get the ground truth predictions at the bottom left, which is kind of showing you what it's looking for. And then, as you can see, it runs about close to 2,000 batches, with the blue line as its training and the orange line is the validation. So from about 0 to about 100, it's training and getting very close to the validation line. But once you get to about 1,000, it's kind of overtraining to the point where it's not getting that, its validation isn't maxing out anymore. And it's a kind of that drop before it jumps back up again. And it starts picking up features potentially, as you can see in the top right, that aren't really specifically, they either are quite damaged sites or aren't exactly what we're looking for. So in summary, as you can tell, we're in that workflow, we're about in the middle where we're doing the ML identification. And for us, it was more of a proof of concept where we had the available data and we wanted to see where it runs in an area where we know there's a lot of earthwork sites under forest that haven't been found. So what we found that ML can increase the accuracy of locating sites across large landscapes. And what we're really keen to do is scale up this approach beyond just using the LiDAR data. And what we potentially want to get to is large-scale 3D reconstructions of the landscape that would be useful for public outreach and just enhancing what we know about the amazing landscape that is Te Tai Tokerau. So to kind of sum up even a bit more is that models are kind of useful for the future. We're using these models to kind of use all the amazing data sets that have already been generated, and I think that stands out from ArchSite as an amazing resource, and this is a new way of using ArchSite. What we've also found is that we're not sure quite often what's happening in the black box. For example, I've got a good quote from a friend of mine, Reno Nims, who says, machine learning is kind of like your pets. They learn from your behavior, but when you pick up your keys, for example, you're not always going to go for a walk. So for us, it's kind of experimenting and figuring out what's the best way, again, to visualize a lot of data for machine learning algorithms to find the sites that we're looking for. And I think, as we know, machine learning is not going to replace archaeologists. It's a very slim chance. We're just getting the robots to do the boring bits so we can do the amazing field survey and find these amazing sites in Northland. And we're at the end. Just want to give acknowledgements and thank you so much to Thomas McDarmond for the 3D model, Ben Collins for soundboarding, Rod Clough for his insights as well, and particularly Matthew Barrett, Reno Nims and Patricia for their thoughts and ideas about the paper, and especially Matthew Barrett for recommending to present it here at CAAA 2021. It's really appreciated. So on behalf of myself and Simon Bickler, thank you for the opportunity to present our research here, and I look forward to any questions you may have.